In this episode, we're looking at how the aerodynamics of a car changes when you brake, and the results are really cool. So, when you look at a car's aerodynamics, is drag coefficient, for example, you really just get one number, but that number isn't really representative of the entire car's drag. It is and it isn't. So that number is literally just for one particular flow condition. It's almost always at just a steady 140 kph. But that isn't very indicative of the real world driving, because when you drive around, you're almost never at 140 kph. And what's more, you're almost never at a constant speed either. You're almost always accelerating, decelerating, and even braking. And during these maneuvers, the car's position to the road changes. During acceleration, for example, it pulls back a little bit, which compresses the rear shocks a little more and tilts the nose up a couple degrees, or maybe a degree or so. On the other hand, during braking, the exact opposite happens. And because a car can usually brake faster than it accelerates, those changes in orientation are usually larger. So, how does the braking process affect a car's aerodynamics? That's what we're looking at today in this podcast. And the braking becomes even more important when you think about how more and more cars are featuring active aerodynamics. So that's when you're under braking and then various things pop up and down. For example, rear wings are increasingly becoming very responsive to the driving conditions, where if you were to accelerate or going at very high speeds, the rear wing will usually be somewhere between completely retracted or in a kind of minimal drag and downforce reduction setting. Then during braking, it will often flip up to almost 90 degrees so that there's this huge frontal area for the air to slam into and decelerate the car. And that is in this paper what we're looking at. The researchers covered this exact thing. So this paper is called, if I scroll up here, a fully coupled analysis of unsteady aerodynamics impact on vehicle dynamics during braking. It's open access and you can find the link below. And the DOI is at the top of just here. So this research is also very interesting in another way, and that is they don't just set the car at one angle that is supposed to be somehow representative of the entire braking process, but rather they actually factor in the forces on the car, the stiffness of it, and then calculate the new position of it during the braking procedure and the associated aerodynamics effects on this position as well, so the forces. And in turn that goes on. So that's called a FSI simulation, which stands for Fluid Structures Interactions, where the fluid affects the structure, the geometry or orientation or whatever, and in turn that affects the aerodynamics, and vice versa it goes. So it just continually feeds into each other and changes the entire aerodynamics overall. And to simulate that is really difficult, especially when it comes to the computational power required to do it. We'll get into that a little bit more later on, but first let's just jump to their setup. So before getting into the car setup, the researchers wanted to test their FSI approach on something a lot simpler to do and something easy to do during experiments as well. So they have something to validate their FSI method with, and then they can go from there into their car and then do it properly. So in figure 2, we see a wind tunnel with a rectangular cylinder spanning the entire distance, or not the entire distance, but some of it. So that's the cylinder there, and that's the general geometry here. The idea is that they suspended this cylinder and then ran the wind tunnel at a certain velocity. The cylinder would then bounce around because the von Karman street forming off of it would then cause different forces, and then that could determine how it moves, and then where it moves to, and at what frequency it bounces around at. Then they could simulate this exact thing in CFD and see how their FSI CFD compared to the experiments. And honestly, even doing just this is quite difficult to do to get it right. So there are a bunch of variables that need to be taken into account, and the authors seem to have done really good so far. So for example, they even looked into the turbulence intensity here, which was 4% in the wind tunnel, and then they set that to the same thing in the CFD. And while you should definitely do that, it's pretty rare to see actually. So in fact, all of our aero simulations that you see, like all the different ones that you see online from all researchers, I'd say that a rectangular cylinder is one of the least sensitive to turbulence intensity, but they still did factor that in, which is great. And the quality of their setup doesn't stop there. For example, they even talk about their decision for their Y plus value in their CFD for this particular cylinder. They say that they chose a Y plus value of around 200 because the cylinder has sharp edges. And that means that the boundary layer separates at a very distinct point at the edges. So let's see these actual results here. If you zoom in here, we're going to go into those in a second. But at the edges, the boundary layer separates very nicely. So the turbulence intensity level isn't really that important because the boundary layer formation is not really going to affect this separation very much. As such, The nuances you would get with a lower y plus value, which would then definitely be important for something like an airfoil, aren't so much important here. As such, a y plus value of 200 is pretty good. And it's true that, especially considering that when you're using a KMedia SST Tempest model, they can then handle the y plus values of around 200, so that's a pretty decent setting. Let's now see how the FSI method fared here. So in figures 3 and 4, we see the results and they look pretty good. So first of all, in figure 3, let's zoom in a little bit here. So in the top left here, we have, let's dismiss this, the AI, who wants that? So first of all, in figure 3, in the left column here, we see the displacement values of the cylinder with time for the experiments in blue and for the CFD in red. They are looking really good to begin with. They're right on each other. Then they start to drift a little bit out of phase over time. Now that drifting could be for a number of reasons, and the fact that there is such good agreement to begin with is very impressive. On the right now, we see the frequency of the oscillations in an experiment in blue and then the CFD in red, and the peaks are almost identical in both frequency and amplitude, so that's pretty impressive. They also managed to get their flow physics down pretty well here. So I'd say that the FSI method looks very much validated. Now in figure 4, we see some of the general flow physics, which has nothing really to do with the car, but it's just of general interest. So as I mentioned earlier, if you zoom in here, you can see that for all these figures, the flow separates at the sharp leading edges, as you'd expect. And you can see that the vortex is being shed over time. So I think we can conclude that the FSI method is good for their idea about how to test the aerodynamics of a car braking. Let's now move on to that setup. So they tested 2 different scenarios. The first was when the rear wing was stationary. So this is the stationary one. It's in the regular position they'd be driving around at. Then it takes into account when the rear wing is flipped up when you press the brake pedal. So that is now when you would have like this active aerodynamics. Some cars have it, some cars don't. So when you press the brake pedal, sometimes it won't pop up, sometimes it will pop up. But how does the aerodynamics affect the car's braking then? And the car itself is a funny choice because there is this massive cutout at the back behind the rear window, and that's going to create a large wake that will potentially hit the rear wing. But I think the reason why they chose this car above all others is that they say that they have a lot of real-world data on it, like braking characteristics and the friction coefficients, the suspension, all that kind of stuff. So it'll be interesting to see how the car performs under braking. Now, we're going to go into discuss very interesting CFD setups to brake this in this braking simulation. Let's look at what they are doing here. So during the braking process, the velocity of the air relative to the car changes. The researchers identified 3 different ways to potentially handle this difficulty when you have to change the air's velocity inside your domain. The simulation isn't like a regular simulation then, and that means that you can't really just set the inlet velocity and forget it. Here, the speed of the air in the domain has to be really analyzed to make sure that it replicates the braking process. So the first approach to solve this problem of changing airspeed when you're braking is that they identified that as potentially solving the problem was to use an MRF, so a moving reference frame. That then accounts for the inertial changes of the air when it changes velocity. But they say that that approach couldn't really be used in Fluent here because this Fluent, particularly at this point in time, I don't know if it can at the moment, but when this was done, Fluent wasn't able to do overset meshes with MRFs. And the reason why they needed an overset mesh was so that the car can move around relative to the ground. So I've explained what an overset mesh is in past podcasts, but just to recap it briefly here, an overset mesh is when you have a regular mesh, just the regular domain mesh as we have here, and then you have a smaller mesh around whatever wants to be moving in the domain. So if you had an airplane that you wanted to have flying around, you'd put that in its own separate mesh. Here is the car. And that second mesh is now overlapping the global mesh. Both meshes exist still. It's just that the little local mesh is just for that little object. Then for each time step, the second mesh can move around, and the information about the geometry and the air in that local domain gets passed to the global domain and vice versa. That way you can take into account the relative motion between these 2 domains. So that way with using an MRF with an overset mesh isn't applicable in Fluent at that point in time. The second way to potentially solve handling the relatively slowing down of the air compared to the car, was to make the global domain so large that it covered the entire braking distance of the car. It would mean that it would need to be at least 110 meters long, because that's how long the car took to decelerate from the starting speed to 0. So this entire domain, instead of being 50 meters long, would be 110. So the obvious problem there is that you'd have to have a lot of cells there, and then coupling that with the fact that they're using an overset mesh, the computational time would skyrocket. So they ruled out that approach. The last possibility is something pretty interesting though. So their description of it is the domain was the same as it was for the steady state analysis, so the car wasn't braking, but the cells were moved with time, so that the flow could then be slowed, I guess. It's an interesting solution, and I wish there was more details about it, but I can't seem to find any more on it than what just that general description. Anyway, this simulation was done with Fluent, and that's a really nice CFD software, but it's very pricey. If you want to learn OpenFOAM, which is just as good but free, then check out our courses below. Anyway, in figure 6, we see the domain, and we can see that they simulated only half a car. And then that yellow plane there, that's the symmetry plane. So that's almost certainly to reduce the number of cells. And the area inside the domain was stationary, and the inlet velocity was 0.2. That actually leads to a very interesting thing when we see the data, as we'll see in figure 26. Let's quickly go down there. We're going to go into it more later on, but I just want to show you something pretty cool with streamlines. The streamlines here look very different to what you're used to seeing, because now we're looking at them from a different frame of reference. And that's something you run into when you're doing overset meshes in stationary flows. The resulting flow fields look very different to what you're used to, and we'll cover that a little bit later. Anyway, the y plus value for their CFD setup here was now between 10 and 30. And we can see that in figure 8 here, actually the y plus values. And these values are again okay, maybe a touch high, but again, because this is quite a high power CFD simulation, that was likely to keep the cell count down. And most of the car is around 20, so that's pretty good. And then in figure 9, we see that not only is the entire car in its own overset mesh, but also the rear wing. So there's a little tiny overset mesh going around there, if you can see. And that makes sense too, because it has to flick up as well, independently of the entire domain and the car as well. So there's an additional overset mesh there that can move by itself relative to the car. They then have a grid converter study here, which is good, and we can see that in figure 10 here. They have the drag force in newtons versus the cell count, and I'm actually really surprised that they could get even such a similar value for 7 million cells as they could for 15 million cells. I mean, they say 7.7 million cells was acceptable as a lower limit, but even 6.6 million cells was pretty good. But then again, it's half a car, so maybe that's kind of okay. That would be like 15 million cells for a full car, maybe a bit more with the unsteadiness. So I guess that's kind of starting to get into the ballpark. Anyway, that is the CFD for the fluids, except for the validation. They'll get to the validation a little bit later, but now let's look into their structures side, so their dynamic model. So in table 4, which is down here, somewhere, here we go. No, that's table 5. Where's table 4? Here we go, table 4 here. We see some values of their dynamic motion, so the sprung mass of the inertia, and the authors use these details and various other things in their model to take into account some of the non-linearities and just the general dynamic motion of the car as it goes along, including even like the slip of the model and like the damping of the suspension and things like that. It's really cool. And how that even changes with different ride heights. So that's really advanced. We see some of that in figure 12, where we see that the damping model is very non-linear to begin with, but as the speed increases of the shrinking of the suspension, I guess, then the dampers get stiffer linearly. Now, one thing that's very interesting to me is that if I'm reading this right, they obviously coupled the CFD with a structural motion, but they say that both of like these two halves, so the CFD and the structural side, each half of those simulations, they were done with the same time step of 0.005 seconds. The data is then shared at each time step, and the solvers can then continue until the simulation is finished. So what that means is that the CFD does one time step, which is 0.005 seconds. Then the data regarding the forces on the car from the air are then passed over to the structural software. The structural software does its iterations to find out how the car's position changes, and then sends that back to the CFD. The CFD then updates the car's position with the overset measures, and then does another time step and sends the data across again, and so on it goes. Now, 0.005 seconds is 5 by 10 to the negative 3, and that's a little high for a car, but given that they used 7.7 million cells, I guess that's around expected. And I'm not familiar with the structural software that they used here. But if it's like other structural softwares, then while a CFD iteration might take like 5 minutes to do, the structural one might take like 5 seconds or even less. It's really much quicker. So adding the structural side doesn't add too much time to the overall simulation time. It's really the passing of information, then updating the CFD, and then running from there. That's quite time consuming. And as I said, I'm not familiar with this structural software. It's called msc.atoms for those interested in it. So that's the computer side. Let's go to the experimental side, because they actually did some experiments to get some validation data, which is really cool. Down here, it's really challenging to get like the car height, etc. in experimental data. But anyway, in figure 15, we see an aerial view of the car's track, and it's just a long straight. Then in figure 16, we see the car with a massive wing at the back. So in figure 17, we see the validation data from their experiments versus their CFD. Let's zoom in just enough, that's good. The blue is the experimental data and the red is the numerical side. What these graphs are literally showing is the braking process of the car from 40.31 meters per second to rest over a certain amount of time. You can see the acceleration is only going from 0 to 1.4 seconds, while the entire braking process went to about 5 and a bit seconds. So they only have the first little bit here, because I guess the acceleration was pretty average after that. Anyway, the simulation results are really impressive. I mean, to get such similar values with any quantities here is very difficult, let alone all of these. The acceleration probably shows the greatest deviations, but in reality, the experimental data probably has quite a bit of noise in it due to the accelerometer. That's the blue line. So we're getting really good agreement here with the CFD. That's good. Then in table 6, we see some numbers quantifying how good the agreement is. So the braking distance and stopping distances are both within 1% of each other, which is incredible. That's really good. Then the maximum deceleration is 5% off, but I don't know, looking at figure 17, perhaps a better measure would be like the differences in the velocity, because you wouldn't have as much noise from the accelerometer, I guess. So like this line on the right here. Anyway, the acceleration looks really good to me, because eyeballing the average of experiments, they look very close to the CFD. So I think that we can say that the model is well validated here, and honestly, better validated than many other CFD simulations, and ones that are much easier than this too. So that's quite impressive. Now in figure 18, we can see some of the effects of flipping the airfoil up when braking compared to having it at the same orientation during braking. So to begin with, the differences don't look like much, they're very similar. But as the time progresses, the car with a movable wing has a much shorter stopping distance. You can see here it's by about maybe 10 meters or so. And that happens because you have a cumulative aerodynamic effect of the wing on the car. So the more you use it, the more impacts the final results. It just adds up over time, where you have a little bit of an effect at the start, more and more and more just keeps adding up just by the sum of little bits. Now in figure 19, we see the forces on the car through this braking process. The solid black line is the stationary wing, the dashed line is the airfoil moving, so when it's flipped up, and then the dotted line is when the angle of the wing was, how it was pitched with time. So immediately in the total lift versus time, so this left figure here, we can see that the airfoil takes a little bit of time to deploy. This dashed line shows it takes about 0.17 seconds maybe, I don't know, 0.15 seconds to completely deploy. That's to be expected. It takes time to do that, especially such a large wing. At the same time, you can see that the total lift drops like a rock. This dashed line, in other words, it's producing way more downforce over all the car and the wing together. And in the bottom left figure, we see the total drag, and the drag more than doubles with the wing deployed. Then as expected, as the time progresses, the car slows and the wing produces less and less force. And the authors divided these forces up more into the, let's zoom out a bit here so we can see. They divided the overall forces into the force just on the car versus the force just on the wing. And interestingly, the car's downforce, so this middle top one here, The car's downforce increases a lot when you deploy the wing, and really far more than the downforce on the actual airfoil itself on the right here. And figure 20 shows us why that is, at least why the car has more downforce now. So in figure 20, we see the pressure coefficient, and the red line is when the airfoil is deployed, and the blue line is when it's just in the regular position. And if you don't know what this pressure coefficient is, then check out a video on our YouTube channel called Pressure Coefficient Explained, Aero Fundamentals number 12. We go through it and the equations there. Anyway, we see here that ahead of the rear wing position, so this back part here, so over the back of the car, the pressure coefficient is much higher. So that means that there is more pressure effectively here too, and it's higher over a flat surface. So that higher pressure is pushing the car into the road more. That's why we get more downforce. And the reason why we get higher pressure here is because the wing flips up and the oncoming air slams into it. It decelerates and the dynamic pressure turns into static pressure that can be felt. So the car benefits far more from this wing being pitched up, at least in terms of downforce, than the actual rear wing itself. In terms of the drag, we can see that the airfoil does produce a huge amount of more drag on the right here, and that's great for stopping. The car also experiences an increase in drag, but it's only about 150 newtons compared to about the 300 or so by the rear wing. So that exact force changes with time because the velocity is changing, obviously, but that's about the average. So overall, I think that you can conclude that the rear wing in this pitched up motion increases the drag a lot more just by itself, whereas it increases the downforce on the car indirectly. So looking at figure 20, this one here, we can see that, the pressure does increase at the back, but there aren't any vertical surfaces here around really that will help with increasing the drag. In fact, the only vertical surface around here is the rear window, and that's in the wrong direction. You have this high pressure on the rear window pushing the car forwards actually. So that high pressure is actually reducing the car's drag, you can kind of see. Anyway, in figure 21, we can actually see the pressure behind the car. So these two little figures here. And with a stationary wing on the left and the moving wing on the right, there is definitely higher pressure behind the rear window with the moving wing. But it's a little hard to tell, but I think that there is slightly lower pressure behind the car too, so in this wake region here. So that could be part of the drag increase reason too. So in the top row, we see the pressures over the car, and the authors have done a pretty cool thing where they stitched together the stationary wing car with a top and then the moving wing car on the bottom of the figure. So we can see both of them at the same time and compare them very easily. So one thing that is very interesting is that with the moving wing, the pressure under the diffuser is much lower. So here you can see there's more green here. So having this wing move around also affects the diffuser. That will also increase the downforce, and that is likely another reason why we saw greater downforce on the car when the wing was deployed in figure 19 here, this plot here. Sorry, this one here. Now in figure 22, we see some of the dynamic responses of the car with time. So the solid line is for the wing in the regular position, and the dashed line is for the wing in the deployed position. In terms of acceleration, there is slightly more acceleration when the wing is deployed, as you'd expect. So it's this dashed line here is a bit lower. But in the middle graph, we see the pitch angle. So when the car brakes, it lurches forward and the car pitches more. With the wing deployed, it pitches forward a little more by about 0.2 degrees or so across the range. It kind of changes again a little bit, but it's about that on average. So what that will actually do is make the car produce more downforce because it is effectively at a more extreme angle of attack. And as long as the flow behaves more or less the same, with no sudden changes in things like separation, then the downforce will increase because the car is pitched down more. So that is yet another reason why the car is producing more downforce when the wing is deployed. Then in figure 23, we see how much downforce there are on the front wheels compared to the rear wheels during the braking process. Downwards force, not downforce. Although I guess it's analogous, but downwards force on the front wheels compared to the rear force during the braking process. So what this means is a greater ratio means there's more force on the front wheels compared to the rear wheels. And with the wing deployed, there is noticeably more on the front wheels, around 5 to 10% more than you'd usually get without the wing deployed. So the front wheels are being loaded more, and that makes sense because if the car is lurching forward more, the car's weight is being thrown forward more onto the front wheels, and it is lurching forward more because the acceleration is greater. And then in figure 24, we see a larger view of the pressures over the car. We see similar things to before where we saw that the bottom half, we have the wing. We have more higher pressure on the boot and on the roof. So that's going to produce more downforce there. Now in figure 25, we see the streamlines over the car, and there are huge wing vortices on the right. Like these vortices cover like half the rear of the car almost. Lol. And in the top left figure, I think we have the wing deployed. The streamlines from underneath the diffuser are shooting up more. That agrees with what we saw in figure 21, where we have more downforce being produced on the diffuser. And so there's lower pressure here behind the car and the wing when the wing is deployed, and that sort of sucks air up from underneath the diffuser and shoots it upwards. That's what I think is happening here. So this rear wing is actually really helping the diffuser perform better during the braking process. Now in table 7, on the right here, we see the overall comparison of the braking metrics of the car with the wing deployed. Now across the board, the metrics are pretty much better when the wing is deployed. The stopping distance is lower, as is the stopping time by about 7%. There's greater deceleration and more downforce by about 60%. Perhaps the only bad thing about this wing is that it's increasing the pitching angle because it's throwing the car's weight forward more due to greater deceleration. That might not be so good for handling. I mean, it depends, I guess, but the fact that there is a dynamic change in the force makes it harder to control. It would also make drifting a little easier because you would alleviate the friction on the rear wheels a little more, so that's nice. Now, the final thing, but really weird thing to see is in figure 26, we see these really weird streamlines. So we mentioned them earlier before, but let's go through them more because they're not what you'd expect. So what is actually going on here is that we're seeing the streamlines from the moving observer's reference frame. So effectively, as the car plows through the air and not as the air flows over the car. As such, this is what it would look like if you could visualize the air as the car travels through it on the regular road. So it's a little hard to interpret because we're so used to seeing like things like 25, the streamlines here, where you can easily see the flow going over the car. It's very easy to understand, it's very intuitive. But in figure 26, not so much. Now in general, we can see a very large wake and a lot of chaotic motion behind the rear window. There's separated flow there. Then over the car, the air is being disturbed, and so upstream you can see these streamlines being curved. That's the car plowing into it and disturbing this air with having these upstream effects. The air over the car is being pulled forward a little, so you can see these slight tiltings of the streamlines here. Then behind the wingtip vortices are just entraining almost all the air behind it. It's having a massive effect on the right here. And the reason why I wanted to highlight this figure is because of how uncommon it is to see this. But if you do overset meshes, then this is very common to see when you process your results. And it's so important to get familiar with them as well, because I'm still definitely more uncomfortable with figure 25, these streamlines here. But it's important to understand those in figure 26 too, because you can see them in a different light, how the flow is moving, and you get different insights. So that is it in this podcast. If you want to learn overfoam, then check out our courses in the link below. And if you like this episode, hit the like and subscribe buttons, and we'll see you on. Peace, amigos.